Okay, the last thing I want to do in section 4.1 is take a deeper look at the extreme value theorem. Because it says that if f is continuous on a closed interval from a to b, then f attains an absolute maximum f of c and an absolute minimum at some numbers in between a and b. Well, what I want to look at is why is it saying that why is it requiring it to be continuous, and why is it requiring this to be a closed interval? Let's talk about this for a second, though. The extreme value theorem, it's like a guarantee. It says if this, then it attains the absolute maximum. So it's like a guarantee. If you satisfy that thing in the purple box, then it's going to have an absolute maximum. Notice if the function doesn't, if it's not continuous, or if that interval is not closed, then all bets are off. Maybe it still has an absolute maximum, maybe not. But this is just saying that if it's continuous on a closed interval, it's guaranteed. Now, what I want to look at is what could go wrong if we didn't have this. So what if the interval wasn't closed? So what if the interval is open? Let's say we're looking at the interval from 0 to 2. Keep in mind what that means is x is between 0 and 2, but it's not equal to either one of them. Now, before we do this, think about this for a second. What's the smallest positive number you can think of? You might think 1, but of course we've got fractions. You could go to 1/2 or to 1/4 or a billionth. The thing is, there is no smallest positive number. Because if I tell you to tell me the smallest positive number, and you say a billionth, I'm going to say 1 over a billion and 1. You know, I can always make it a little bit smaller, or I could say 1 over 2 billion. You know, that's half the size of 1 over a billion. So there's no smallest positive number. And another thing is, what if I told you to tell me the biggest number? Well, there is no biggest number. You know, any number you give me, I can just say twice that, and I've got one that's bigger. So there is no largest number, and there is no smallest positive number. Another thing to think of is, on this interval right here, there's no smallest number in that interval. That goes right back to what I was saying about the smallest positive number. There isn't one. You pick any number in here and you try to make it the smallest one, I can cut it in half. Or if you say I'm going to go with 0.000001, I can just always put another 0 in front and get a smaller number. And what's the biggest number in this interval? Well, the same thing's going to happen. If you try to give me the biggest number in this interval, 2's not in there, remember. So you could say something like 1.9999 and then spend a few hours writing out a bunch of 9s. But it's still not going to be the biggest number in there. I can come here on the end, put another 9, and I've got a larger number. That's the reason that the interval has to be closed. Let's say we had the function. Let's say we were looking at f of x equals x squared on this interval from 0 to 2. I could graph this like this. I could put an open circle down here at 0 and an open circle up here at 2, 4. And so there is no absolute max there because it doesn't actually get to that 0.24. You might say, well, why don't we just call 4 the max? Well, because it's not included in the in that graph. Those 2 open circles are not included. Now, 4 is an upper bound for this, and there's a name for that called the supremum. And down here, at this point 0, 0, there's a name for that also called the infimum. But any point that you pick on this graph, I can pick one that's a little bit closer. And so there is no absolute max or absolute min on that. Okay, what about this? Why is the function required to be continuous? Well, because if it's not continuous, it's possible to construct a function that's not continuous on a to b and has no absolute max or no absolute min. Here's an example. Let's say a is 0 and b is over here. This function, I'm going to change my b slightly just to make something obvious. All right, so if we've got this function between a and b, it has an absolute max but no absolute min. The absolute max is going to be right here, but it has no absolute min because over here we could approach that point, and whatever the y value of this open circle is, that would be like the lower bound, but we could never actually attain it, so the minimum doesn't exist there. And you can do similar things with other types of discontinuities. Let's say you had a parabola, but it had a open vertex at the top. So that point's not there. If I make my A here and my B over here, then let's see, we've got a few points of interest. This would be the absolute min on the interval from A to B. And there is no absolute max because the point here at the vertex is missing. So anyway, that's why it's required to be continuous and required to be closed. You need both of those if you want to guarantee that you have both of the absolute max and the absolute min.